Greek letter rho, right? Rho in the ring. Then, because these two belong to this subset, X R and Y R both belong to U for every R belonging to R. Which implies X minus Y times R, which is nothing but XR minus YR, which also belongs to U. Why does it belong to U? Because U is an additive subgroup, so the difference of these two subgroup elements is again an element in the subgroup. For every ring element. Thus, X minus Y belongs to this, that is, this is a subgroup of R under addition. Okay, so next thing we have to show is that rho X and X rho are both in this subset. Okay, so next, rho XR. So X rho will be easier to show first. Next, X rho R. Now this is our element rho that we have chosen in R, and this is again, this small r is again a ring element. This is equal to, by associativity of multiplication, rho R belongs to U for every R belonging to R. Okay, what is happening here? X rho R, that is equal to X times rho R, there is no doubt about that. But what is this? Since rho and R are both ring elements, their product is also a ring element, and according to our condition, if I multiply X from the right side by any ring element for every R belonging to R, the result is in U. Here I am multiplying X by this particular ring element, rho R. That is also in U, and this is true for every ring element R in R. So what have we shown? We have shown that if we multiply this element X rho by any ring element, the result is in U. And that is precisely the condition for X rho to be in this subset by its definition. So, X rho belongs to the subset. And now what is left is to show that rho X also belongs to this. Next, for any R belonging to R, we have X rho R, rho X R, okay, rho X R is equal to rho times X R. Right, okay. Now what do we have here? XR belongs to U. Okay. Yes, this belongs to U. Why? Since XR belongs to U. or let us just write the condition afterwards. This is true. Oh, we have already taken any R in R. Okay, fine. Since XR belongs to U. Where is this coming from? This is coming from the fact that X belongs to this set. That's why XR is in U for any ring element R. So since XR belongs to U and U is an ideal. So if I multiply this ideal element XR by an arbitrary ring element rho, this product will belong to U. So that's why this belongs to U. So here again we have shown that rho X times any ring element belongs to U. So according to the definition of this subset, rho X belongs to this subset. Hence, rho X belongs to this subset. This shows that this is an ideal of R. But we are not done yet. We still have to show that this ideal contains the ideal U. Okay. Note that for any U belonging to U, we have UR belongs to U for every ring element R, and this is simply because U is an ideal. So if we multiply U by a ring element, I mean any element of U by a ring element, the product will belong to U since U is an ideal. Okay, although I am saying describing the things quite fast, you have to carefully go through all the steps because things may get confusing. Why something is true, you just go through it. When you go through this video, pause it quite often and try to think through it, what we are saying. Okay, don't take my words for anything. You just see. If something is not clear to you, you can ask in the comment later on. But go through everything and see that whatever we are writing here, everything has an explanation, a reason for it. Okay, it has to be logical since U is an ideal. Okay. So now what have we written here? If I multiply any element in U by this ring element R, any ring element, then UR belongs to U. So this U it satisfies the condition to be in this subset, which now has been shown to be an ideal. So U belongs to RU. This proves that U is a subset of RU, and that completes the solution. So this is not just an ideal, but it contains this one as a subset, this ideal with which we started. Okay. Now these exercises have been of somewhat similar nature. We are taking a ring and then somehow we are generating an ideal inside it. And the next one, however, is slightly different. It also involves a general ring, but it asks us to create another ring, not just an ideal, using the ring that we are already given. Let R be a ring with unit element. So R is now not just any ring but a ring with unit element. Okay, so using its elements, we define R tilde by defining A plus B equal to A plus B plus 1 and A dot B is equal to A plus B plus AB, where A and B are elements in R and where the addition and multiplication on the right hand sides of the above relations are those of R. Then we have to prove these things. A. Prove that R tilde is a ring. Okay. Is a ring under the operations and not. Okay, B, part B says what acts as the zero element of R tilde? It's a question. Just like that. What acts as the unit element of R tilde? Okay, so R tilde has a unit element also, and we have to find it. Prove that R is as okay. And lastly, prove that R is isomorphic to this new ring. So first let us see what we are being asked. We are given a ring R, okay, and it of course has an addition and a multiplication, where we are not really using any symbol for multiplication, as is the common practice. We denote the addition of in the ring by this plus symbol, and that is, we will write the sum of two elements like this. If A and B are ring elements, then their sum is written like this. And their product, which initially we wrote like this, we later dropped this dot because it serves no purpose to write dot. One operation we are using a symbol, another one we can work without using any symbol. Okay, that is fine. Now we want to create a new ring. So to distinguish between the already available addition and the new addition, we are using a different symbol, a different plus. Just like that, to distinguish between the two multiplications, our new multiplication, now we are writing it using that dot. And what is R tilde? Although we are using a different symbol for the ring, it's going to be a different ring, but the underlying sets are equal. This also is after all a set along with two operations. The new ring also will have the same elements in them, but the definitions of addition and multiplication are different. Now sum of A and B means A plus B plus 1, and product of A and B means A plus B plus AB. And these plus and dot what we have on the right hand side of these relations, they are the operations already available in the ring R. Okay. Now in this setup, first of all we have to of course prove that this R tilde is a ring now under these two new operations. Then we have to figure out what is the zero element of R tilde. This of course will be only a part in showing that R tilde is a ring, because we have to figure out the zero element. And R tilde supposedly also has a unit element. Note that our original ring R is given that it has a unit element. Now we have to find the unit element in R tilde also, and lastly we have to prove that these two rings are actually isomorphic. That is, in ring theoretic sense, they are one and the same. Okay, so we have to go through these steps. So let's look at the first one first. So we start the solution.